I'm going to explain you about the Kundts Tube. This will be our apparatus of Kundts Tube. We need to measure a velocity of sound from this experiment, and along with that, additionally we will calculate a adiabatic coefficient gamma of air at room temperature. So this will be the apparatus, consists of a perpex tube, long perpex tube, on which at one end there is a loudspeaker and there is a movable rod consisting of a microphone. Along with this, we will be using a signal generator having different waveforms and a range of 0.2 to 200 kilohertz we can use from this signal generator, and there is a attenuation knob which won't be using in this experiment, but you can adjust a signal amplitude from this. And there is a digital multimeter for this experiment. Here it will be used to note down the voltages, but apart from this you can set the frequency which we will be doing in this experiment. Apart from this, you can determine the resistance part, temperature, voltage in AC or DC, everything. So coming back to the experiment, as I mentioned, there is a loudspeaker and a microphone. So when we set a particular frequency from this audio signal generator, it is given to the loudspeaker, and because at the other end of the movable rod there is a microphone, that range of different frequency what we have set will pass through this, and in this experiment will be giving sinusoidal wave. So this sinusoidal wave will consist of antinodes and nodes, and this will be a progressive wave. So because of the microphone, it will be reflected back. For the experiment, we will be giving a sinusoidal wave and will set the frequency to 1 kilohertz. This will pass through the tube, and from the loudspeaker it will move further, but because of the loudspeaker it will be converted into a sound wave which is a progressive wave consisting of antinodes and nodes. But at the other end of the movable rod there is a microphone which won't be allowing that to be progressive, so it will be reflected back, and due to this a standing wave pattern, that is a stationary wave, will be generated between these two in the form of sound, and that sound can be converted into a AC signal using the DMM, which is connected at the other end of the movable rod from these two cords. So first of all, I will start with the procedure, and so first of all we will set the frequency from the signal generator and DMM. So we use a VNC cord and connect it over here. And we will be connecting the polarities and set this to kilohertz. Switch on the function generator. We will set approximately 2.4 from this dial. Now the frequency is set, so we'll remove that and connect the Kundts tube to the DMM for noting the AC voltage signal of the sound waves, which is given by the mic and which is converted into a AC signal and detected by the DMM. Now we will shift this to the voltage. We will set the range to 400 m. That is, it will noting the maximas of antidotes and nodes, maximas and minimas in this range only. That is the millivolt. We will connect this cord again. Now, as we have already set the frequency, we can note down the position of the maximas using the DMM. There is a cut over here on the movable rod. This will indicate the positions of the maximas. Whenever we will get the maxima from the DMM, we will note down the positions and corresponding voltage. We will start moving the rod. Whenever maxima will occur, it will reflect over here. And the main thing over here is we need to slide this very gently and continuously in a flow only we will take readings, because every time we will go, it will change the reading and damping will occur. So I will start sliding that. So reading is changing. From the 1.3 it start decreasing. So this is our first maximum. And corresponding position of the maximum will take the distance from this point to the cut mark and will note down. So the tabulation for this experiment goes like this. In the first column we'll have excise, that is number of maximas. We'll be having at least 6 readings, 6 maximas. After that we'll be noting the position yi in centimeters. And corresponding voltages in millivolts. So the same way, by sliding we will get 6 maxima reading. And after that we need to calculate xi, yi. That will be again in centimeter, and we will calculate sigma of xi, yi. After that we need to calculate sigma xi square and summation of xi square. Now in this experiment we will be calculating a theoretical slope using the formula m equals to sigma xi yi by sigma xi square. Gives me theoretical slope. With the help of this m, we will calculate di, which is yi minus mxi, and di square and sigma di square. From this sigma di square, we will be calculating error in slope delta m, which is sigma xi square sigma di square by n minus 1. So we have all the required data for finding the velocity of velocity of sound, that is v velocity equals to mu lambda, where lambda is 2 times of slope, because when we plot xi and y's plot, will have a straight line and the slope will give me this slope will give me the consecutive distance of the positions of maxima. So the lambda will be 2 times of slope, right? So this will give me slope and lambda of a particular frequency which we have said, that is 2.4 kilohertz. Now the error in velocity will be 2 times of mu delta m1, that is of this, and the adiabatic coefficient gamma is v square arm by RT, where m is the molecular weight of air, that is 28.8 gram per mole. R is the gas constant, this is 83.314, and T is the absolute or room temperature. So we will have velocity, gamma and lambda for a particular frequency. The same thing we'll do for another frequency. Let's say f2 is now the same thing will be repeating for another frequency, say 2.6 kilohertz, and again from the readings and everything we'll be having m2 slope of this frequency, lambda 2, v2, delta v2 and gamma 2. So this and this error will be a proportional error, or you can say a individual error of the particular frequency. Now we will calculate a random error, which is half of v1 minus v2, and from both the frequency we will calculate average of gamma, average of velocity, and using these three we will calculate error in gamma, which is 2 times delta v by v and into gamma. So this will come from here, this will come from here, and this gamma is this thing. Now after calculating gamma, we will draw the corresponding least square fit line for each frequency on a graph sheet before plotting our data points. So as you can see over here, we will be plotting xi, that is number of maximas on x-axis, and position on y-axis, and we know the equation for the straight line, that is y equals to mx plus c, and here we will be considering c to be 0. So we have the theoretical slope for a particular frequency m and the number of maxima. So we can calculate the corresponding yi for different xi's, and we will be plotting that on the graph sheet, and that will be our least square fit of that particular frequency. Also, we need to plot our data points which we have experimentally brought, that is our readings yi and the xi's. So these scattered points will be getting through our data points. So you can verify how your experimental plots are matching with the least square fit, or how it is deviating from the fitted line. The same will be repeated for another frequency that we have considered. Suppose this is for 2.4 kilohertz, then you need to repeat the whole process for another frequency, that is 2.6 kilohertz. So you will be having two plots for different two frequencies. So your result will be the velocity of the sound will be given by v plus or minus delta v, the unit meter per second, or you can convert that into centimeter per second. This is the first result, and second you will write down the adiabatic coefficient value, that is gamma value. This gamma with the error in gamma having no value, no unit. So the precaution which you need to take care of in this experiment is main thing. First of all, you need to set the frequency, and once you have set the frequency with the digital multimeter, you need not to disturb throughout the experiment, and this range should be kept in 1 kilohertz, and now and then you need not to disturb this, and the attenuation knob will be at minimized position for the experiment. And for this particular experiment, the frequency should not exceed beyond 3 kilohertz. Also, you need to get your circuit checked by the instructor, and while taking the readings, you will slide the movable rod very gently, and will note down the maximas in a continuous manner in one go itself, and very smoothly you need to rotate, and the position from the cut mark to this point should be noted carefully at each maxima. So these all things you need to make sure while doing the experiment. Otherwise you need to repeat all the readings, because damping will be there every time.